Hello everyone and welcome to The Explainer. Today we are diving into one of the absolute most fascinating challenges in modern AI, which is how on earth do we actually evaluate large language models? We're going to be looking closely at a really powerful metric called BERTScore. Specifically, we'll break down the logic behind BERT embeddings, exactly how they measure actual AI performance, and step by step how this whole system works. But right off the bat, let's just set the stage here. Think about this question for a second. How do we accurately evaluate an LLM's prediction against the actual ground truth? I mean, it sounds super simple, right? You just check if the AI spit out the right words. But mathematically checking an AI's homework against a reference text is honestly a pretty tricky and lengthy calculation. Human language is incredibly nuanced. If we're only looking for exact word matches, we completely miss the actual meaning of the sentence. We really need a way to mathematically capture semantics. So here's our roadmap for today. We'll be covering 1. Evaluating LLMs with BERTScore, 2. Tokenizing the text, 3. Generating BERT embeddings, 4. The cosine similarity matrix, 5. Finding optimal matches, and 6. Precision, recall, and F1. We are going to trace exactly how a simple sentence gets transformed into a highly accurate quantifiable score. Okay, let's jump straight into Section 1, Evaluating LLMs with BERTScore, moving beyond simple word matching. You see, BERTScore is a total game changer precisely because it relies on deep semantic understanding rather than just doing a shallow count of identical words. To really anchor this in reality, imagine our reference text. The absolute ground truth we wanted the AI to say is the cat sat on the mat. But the text actually generated by our LLM is the cat was sitting on the mat. There's a slight variation there, right? An old-school rigid system would actually penalize the word sitting just because it isn't sat. But you and I both know they mean essentially the exact same thing. This is the exact problem BERTScore is designed to solve. Moving on to Section 2, Tokenizing the text, breaking sentences into readable units. While before the model can evaluate these slightly different sentences, it has to break them down into bite-sized pieces. To do that, we use the word piece tokenizer. You see, we can't just feed raw English text into the model. Instead, we take both our generated text and our reference text and we tokenize them into smaller subword units. Then we convert those units into numerical token IDs. These little numerical IDs are the actual language that the BERT model understands. All right, Section 3, Generating BERT embeddings, capturing semantic meaning. Now, this is where the logic behind BERT embeddings really shines, and where the real transformation takes place. We take those numerical token IDs and feed them directly into the BERT model, which generates what we call dense semantic embeddings. The underlying logic here is just brilliant. These embeddings map words out into a massive, multi-dimensional space based purely on their context. Because of this, the embedding for our generated word sitting and the reference word sat will mathematically cluster right next to each other. The math reflects that they are highly related in meaning, even though they're spelled entirely differently. This step right here is the crucial foundation for everything else we're going to talk about. Which brings us to Section 4, the cosine similarity matrix, mapping the semantic relationships. Now that we have these incredibly rich semantic embeddings, we need a way to map out all their relationships. We do this by calculating the cosine similarity between the embeddings of the generated text and the reference text. And we do this for every single token, which forms a giant, complete similarity matrix grid. It's almost like a huge spreadsheet. We check a generated word against all the tokens from the reference, creating intersecting scores. So for example, the cosine similarity between the generated word sitting and the reference word the might be a really low score, something like 0.3, because semantically, a verb and an article just don't share much meaning at all. Let's look at Section 5, Finding Optimal Matches, the greedy algorithm in action. Okay, so we've got our similarity matrix packed full of cosine similarity numbers, but now we have to find the absolute best pairings between the two sentences. To pull this off, we implement a greedy algorithm, and the process is actually beautifully straightforward. Every single word in the generated text basically searches the matrix to find its absolute best match, meaning the highest cosine similarity value, from the reference text. Once it finds that highest value, boom, it forms a matching pair. The ultimate goal of this entire matchmaking process is to maximize the overall similarity score across the whole board. But there is one very strict rule to this optimal matching game. The algorithm ensures that each generated token matches with at most one single token in the reference text, and vice versa. You absolutely cannot have a single generated word pairing up with multiple words from the other text. It's a strictly one-to-one optimal matching scenario. Finally, Section 6, Precision, Recall, and F1, calculating the final BERT score. So, this brings us to the final calculation stage, where we turn these optimal pairings into our ultimate evaluation metrics. For BERT precision, we just take the sum of all the cosine similarities from those optimal matching pairs we just formed, and we average them out by dividing by the length of the generated text. Simple enough. For BERT recall, we take that exact same summation of paired similarities, but this time we divide it by the length of the reference text. And then finally, calculating the BERT F1 score is super easy and very similar to standard statistics. We just combine the precision and recall together to give us one comprehensive metric. And that really leaves us with this final thought. We've seen how going from simple tokens to deep semantic embeddings and mathematically aligning them using cosine similarity allows us to actually evaluate meaning rather than just matching characters on a screen. So I'll leave you with this question. How will sophisticated embedding-based evaluation like BERTScore fundamentally change the future of AI development? I mean, when we can truly measure if an AI actually understands the assignment rather than just mimicking it word for word, the possibilities are practically endless. Thank you so much for joining me for this explainer. Keep asking those great questions, and I'll catch you next time.